Hi, I'm Tom Prettyman. I'm from the Planetary Science Institute. Title of my talk's What's Inside the Earth? How Asteroid Missions Could Help Answer This Question. I'm going to compare and contrast the interior of the Earth with that of small bodies in the solar system, and I'll do this through the lens of two asteroid missions, the NASA Dawn mission, which explored the two largest bodies in the main asteroid belt, and the Psyche mission, which is in development. This work is supported by a NASA virtual institute called TREX and the NASA Discovery Program. So let's start with the Earth's interior. The presence of a core within the Earth has been known for about 250 years. And this was done using the gravimetry. And in the 1770s, in the famous Schiehallion experiment. And the gravimetry was used to estimate the mean density of Earth, and that was compared to the density of crustal rocks. And from that, it was inferred that there was a central mass, and it was further inferred that that mass would be iron-rich. Since that time, seismic measurements have revealed Earth's interior structure, and this is supported by geochemical investigations and other geophysical observations. And so the Earth can be divided into two parts, an outer rocky layer and the inner core, which is metal. And the more detailed measurements that we have today can subdivide that structure in more detail. There's the outer crust, upper mantle, lower mantle. The core itself has two layers, a liquid outer core and a solid inner core. The pressures and temperatures inside the Earth are very high, so high that it's only been recently that we've been able to replicate those conditions in the laboratory. So the two-layer core, again, solid inner core, liquid outer core. The liquid outer core is about 2,000 kilometers thick. You can see that from this table here, which also shows the density ranges for these coarse layers that I've identified. And the liquid outer core is often thought of as Earth's largest ocean. The core is mostly iron and nickel with a little bit of light elements. The outer core is responsible for Earth's magnetic field. So it's generated there via a dynamo process, and convection of conductive fluids driven by energy released by the solidification of the inner core produces the dynamo. Rotational effects organize fluid motion into columns, and these result in the dipole field that we see. So if you're out in the woods with your compass, just remember that you're being guided by Earth's largest ocean beneath your feet. So what's the core made of? To get at that requires a bit of geochemistry. I have this kind of word equation here that says bulk Earth equals silicate or rocky Earth plus core metal. And if you knew two of these terms, you could solve for the other. And it turns out that we can get at silicate Earth from mantle samples that come up with volcanic eruptions, for example. And we can get at the bulk Earth, the left side of the equation, from analyses of primitive meteorites. And that allows us to solve for what's in the core. And what we find out is the core has about 85% weight iron, 5% weight nickel, so about 90% weight metal. And that's alloyed with these light elements that are shown here. I'll focus in on one of them, sulfur. About 2% sulfur is expected to be in the core. And sulfur is important in determining some of the physical properties of the core, and that puts constraints on the inner workings. So let's continue on. Formation of the Earth. Earth grew by the accumulation of smaller bodies. One is shown here, colliding with proto-Earth, which I'll talk about in a moment. This was a gradual process, but gradual means that it took place in less than about 100 million years from the beginning of the solar system. And the beginning of the solar system is on the order of 4.6 billion years ago. Big impacts, including the moon forming collision, the collision that formed our moon, would have produced large scale melting. And so that's what's depicted in this diagram. This is the so-called deep magma ocean model, and we have an object colliding with the Earth. And Earth at this point is a magma ocean on top. These are silicates. And what happens to a small body, which may itself, by the way, have an interior structure, it might have a core. What happens to that is it whacks into this outer layer, breaks apart. Its silicates are incorporated in this outer layer, and then the interior, which might be iron, forms droplets, and these droplets kind of float down into a metal pond. And then over time, you get drips going into the core. So this material propagates into the core. And so Earth went through this protracted development. This is kind of what might have happened late in the development of the Earth, where the pressures were getting high, and you get minerals that form under these conditions. So one question is, we have these objects that form the Earth. We think of these as building blocks. Are there any of these around today that we might look at? And the answer is yes. So here's an artist's depiction of the early solar system showing a collision. And the point that I'm trying to make here is that 4.5, 4.6 billion years ago, the solar system solids were forming. They were growing into small bodies, and the small bodies were combining together to make planets. And there were a lot of collisions. And in fact, as testament to those collisions, we have this chart. These are 620,000 minor planets plotted, and we're looking at their distribution in terms of diameter, ranging from 1 kilometer to 1,000 kilometers. And what you can see is there are a whole lot of small bodies, and you've got this kind of parallel distribution with a tail. And basically, this is what you would expect if you had a collisional environment. You've got a lot of fragmentation. And so these fragments came from larger bodies. Some of them are way out beyond this tail. This is a dwarf planet Ceres. Just to give you an idea how large dwarf planet Ceres is, you can fit the profile of New Mexico onto its figure. It's about 1,000 kilometers in diameter. And the next largest body in the main belt is the asteroid for Vesta. And these bodies are likely largely intact. They may have had collisions, but they weren't broken apart, and they didn't end up contributing to this distribution here, except for maybe the very, very smallest diameters. Now, right at the edge of this tail, where you have smaller diameters, you have bodies like 16 Psyche that have probably undergone significant modification by collisions. And we'll talk about what that means in just a moment or two. Okay, so the NASA Dawn mission explored Vesta and Ceres, and we actually went to visit them with a robot, and that's shown here. This is the Dawn spacecraft. Dawn used solar electric propulsion, so you gather light with big solar panels from the sun, convert that into electricity, and you have a tank of xenon, and you ionize the xenon and fling the ions out the back, and that produces a very low thrust, but you thrust continuously, and that allows you to spiral out into the solar system to visit and circle your targets. So here's the timeline for Dawn. Launch was September 2007. We spiraled out to the orbit of Mars and did a gravity assist in 2009. And then finally, we reached Vesta, our first target, in July of 2011. And we stayed there until September of 2012 and acquired all kinds of interesting data, some of which I'll talk about. We later transitioned over to Ceres, spent the rest of the mission there. The mission ended in 2018. So here's a picture of Vesta as seen by Dawn, lots of detail. Based on Dawn's mission to the asteroid belt, we now think of Vesta as a building block. We now think of it as kind of like Earth. It would have formed more quickly than Earth. The earliest melts, the earliest magmas that we had in the solar system formed within 10 million years of the beginning the solar system. And you would have had at that time a heat source. This would have been aluminum-26, and it was probably injected into our solar system by a nearby supernova. And that would have heated small bodies, allowing them to melt, perhaps entirely. And then when that source went away, they cooled to form a differentiated structure, core, mantle, and crust. For that reason, we like to think of Vesta as the smallest terrestrial planet. So one of the key results of Dawn was to confirm that Vesta is in fact the source of a group of meteorites called the Howardite, Eucrite, and Diogenite meteorites. And these would have originated by impacts into Vesta's crust and upper mantle. But otherwise, Vesta remained intact. Many of the observations that we have of Vesta are compatible with a magma ocean scenario similar to what I described for Earth. And what's really cool is remnant magnetism in a Eucrite meteorite provides evidence for an ancient dynamo, which means that Vesta likely formed a liquid metal core. And from this information, we can sort out what's inside. For Vesta, imagine that we could reproduce the gravimetry measurements that we made, or that were made on Earth back in the 1770s, except this time we have very high precision measurements of Dawn's gravity field with a spacecraft using radio science. And that information is used to constrain bulk density and interior structure. The data are consistent with an interior mass concentration, and you have core sizes that range up to about 120 kilometers. So structure shown on the right, we think there is probably a crust, a mantle, and core. We have geochemical constraints as well, and those geochemical constraints based on mineralogy, based on elemental measurements by Dawn, give us a sense of what's inside. The crust is going to be basaltic, and the mantle will consist of ultramafic materials like olivine and pyroxene, and the core would consist of iron, nickel, metal, and possibly alloyed with sulfur, perhaps even a lot. In fact, some of the models indicate that you might have as much as 10 weight% sulfur, which would be a lot more than we have in the Earth. So wouldn't it be neat if we could actually see the core? Well, for Vesta and for the Earth, the core is completely inaccessible. However, those collisions I was talking about could lead us to be able to look directly at the core. And that's the theme of the Psyche mission. The logo is up on the left. It's subtitled Journey to a Metal World. And there's a nice illustration of a collision for you to look at. So what's Psyche all about? Well, if we're considering the possibility that we might find a core when we visit 16 Psyche, then that could have occurred as the result of a stripping event where you have a hit and run collision with a body like Vesta, and you completely remove in that collision all of the outer silicate layers, leaving metal. And if that happened early enough and the core was molten, you would end up with a molten blob of metal rotating around in space. And as this core freezes, it would probably freeze from the outside in. You would have currents flowing in the interior, and that could result in the production of a dynamo. So you could have a magnetic field, and the magnetic field could be encoded, if you will, or frozen into the outer metal layer. All kinds of interesting things could happen in this scenario. For example, if you had a sulfur-rich core, you could have sulfur volcanism, which is illustrated on the far right. And so you can imagine sulfur minerals spewing out onto the surface. And that kind of scenario is depicted in this artist's conception. Here's Here's what we think 16 Psyche might look like if it was a stripped core. The metals are here. You can all kinds of interesting impact features. Maybe this region here is the sulfur that flowed out onto the surface, or maybe it's just remnants of the inner mantle that are still present. So why Psyche? 10th largest asteroid in the main belt. Its optical and radar reflectance data suggest a largely metallic body. Its density is consistent with high metal fractions, and so we might be looking at a stripped core. The other nice thing is it's accessible by a NASA Discovery mission, which is what Psyche is. So Psyche spacecraft, a lot like Dawn, built by a different company. It has about a 25-meter wingspan, so to collect the sun's energy, convert it into electricity. We have electric propulsion through Hall thrusters, and that allows us to get around the solar system. Very simple payload to answer the key science questions that we have. Certainly we'll want to have a magnetometer and to measure the magnetic field. We have a gamma ray and neutron spectrometer to measure the elemental composition of the surface, looking for sulfur, looking for nickel, looking for iron. And then we have a multispectral imager. The multispectral imager gives us very detailed photographs of the surface and also tells us a bit about the mineralogy of surface regions. So the timeline for the mission launches in August of 2022. So we're still very much in development. Following launch, we spiral out to Mars and we encounter Mars in 2023. And then ultimately we're captured and go into orbit around Psyche in 2026. End of operations happen in October 2027. Very much looking forward to this. So Psyche's a mission to a metal world. It transforms a blurry point of light into a geologic world, much like the Dawn mission did for Vesta and Ceres. It also explores the interior of a small body that represents the building blocks of Earth and the terrestrial planets. And if it is metallic, then we might learn things about planetary cores by looking at one directly. So this complements efforts to understand terrestrial cores through laboratory experiments and meteorite studies. So to wrap up, I just want to tell you a little bit about how to get involved if you're a student. Nationwide, there are opportunities to participate in capstone projects. There are programs like Psyche Inspired. All of these, by the way, are run by the Psyche project out of ASU. Psyche Inspired is a more creative program that can involve art. And also there are courses that one can take online for free through the Innovation Toolkit. And the way to find out about all this is through this URL, psyche.asu.edu. Get involved. And if you're a student or not, you can get involved by following us on social media at Mission to Psyche. We have programs where you can share your art. If you do arts and crafts, if you have Psyche inspired art, you can share it with us. You can download 3D models. You can read mission team blogs as we go along and learn about the mission. So I hope you can find a way to participate in the Psyche mission. I appreciate your time and I thank you for your attention.